Okay, so here's the definition of the Laplace transform again, written up top, and then we're going to start actually building them out. So the first one, I just want to find the Laplace transform of 1, which just means let f of t equal 1. So the Laplace of 1, by definition, 0 to infinity, e to the negative st times 1 dt. I'm going to write it this time, but I'm not going to keep writing the fact that what we really have to do, because you're not supposed to have a limit that's infinity, is take the limit as b goes to infinity, 0 to b, e to the negative st, dt. So I really don't need to keep writing that 1 in there. So when I integrate that, because I'm with respect to t, I get negative 1 over s, e to the negative st, and that's the limit as b goes to infinity, 0 to b. And I just want to write it all put together before we look at our limits of infinity. So I can just bring that e to the st down. And now when I take the limit as b goes to infinity, I get negative 1 se to the sb plus 1 over s when I evaluate it at 0. So this term, as b goes to infinity, is just going to 0. So I'm left with 1 over s, and s has to be greater than 0. So the Laplace transform of 1 is equal to 1 over s. If I had a Laplace transform of 4, it would be 4 over s. So the general for any constant, the Laplace transform of that constant is equal to k over s. And that is our first Laplace transform. Our next example, I want to find the Laplace transform of t. So again, the formula is integral from 0 to infinity, e to the negative st times our f of t, and our f of t in this case is t, dt. So we're going to need integration by parts to do this. So we start with our t, derivative is 1, then that derivative is 0. And we start with e to the negative st. When you integrate that, we get negative 1 over s, e to the negative st. And then when we integrate that, we get positive 1 over s squared, e to the negative st. And we know that those go on the diagonal. So the integral of that would be negative t over s. When you multiply these two, e to the negative st minus 1 over s squared, e to the negative st, from 0 to infinity, or 0 to b, and take the limit as b goes to infinity. So again, I just want to rewrite it before we start evaluating. So that's negative t over s e to the negative st minus 1 over s squared e to the st. Oops, should be positive. E to the st from 0 to infinity. So remember, this is in terms of t. So when I evaluate this at infinity, this term se, that's just going to go to infinity. Oops. All right, let me do that again. Negative infinity over se to the infinity. So that's a problem, right? That's an indeterminate form. So we can apply L'Hopital's, and then that derivative on top is just going to go to 1. And then we get 1 over infinity, so that term's going to go to 0. When I look at the second term, 1 over s squared e to the st, that term is also going to go to 0. So both of these terms go to 0 when I evaluate it at infinity. Now when I evaluate it at 0, this first term goes to 0 because I would have negative 0 over s. And then the second term, when you plug in 0, we get 1 over s squared. And remember, these were subtracted, so because of this. So we end up with just 1 over s squared. So our first Laplace transform was 1, and we got 1 over s. The second Laplace transform was t, and we got 1 over s squared. And I'm not going to prove this one out because it's long, but the Laplace form for t to the n, so for any exponent, it's n factorial over s to the n plus 1. So those are our first 3 Laplace transforms. So let's do an example of this third one. So if I had f of t is equal to t to the 5th, that means my n is equal to 5. So the Laplace transform of t to the 5th is going to be 5 factorial over s to the, oh, these are terrible, s to the 5 plus 1. So 5 factorial is 120 over s to the 6th power. Don't worry, I'm going to work on my 5's and s's for this section.